Good afternoon, everybody. Thank you for joining our webinar today. This webinar will be focused on addressing issues with lamp quality that you may be struggling with in your instrumentation and analytical device. Today's speaker is Lauren Loudon. He is our OEM product and business development manager. He's very versed in this area of technology. A few housekeeping things before we get started. All lines have been placed on mute to prevent any background noise. If you experience a technical difficulty during this webinar, you can contact me through the chat feature. This webinar will be about 45 minutes in duration. At the end, we will have some time for questions and answers, and you can submit your questions through the Q&A chat box at the top of your screen. You can submit your questions at any time during the presentation, but we will be addressing them at the end of the session. So with that, I'm going to pass it over to Lauren.
Thank you, Maria. Hi, everyone. Good afternoon. Thank you for joining us today. This is the second session of the day, and so I'm happy to have all of you with us. Again, the title of this webinar is Struggling with Lamp Quality Issues for Your Analytical Instrumentation, and how Labsphere and ILT may be able to help. So while the primary goal of this webinar is addressing, quality issues for illumination sources going into analytical instruments and medical devices, if you're working in general spectroscopy or radiometry and photometry applications, there's going to be a lot that applies to you as well. So, just keep that in mind as we move forward. And again, my name is Lauren Loudon. I'm the OEM Business and Product Development Manager at Labsphere. I've been with Labsphere in a variety of roles for several years, and this is where I find myself today. And so just to kind of kick us off, for those of you that don't know, Labsphere and International Light Technologies merged back in April of this year. And so the really nice thing about that is it brings two authoritative brands with radiometry and photometry experience together. And, while Labsphere and International Light have always have focused in slightly different areas of radiometry and photometry, there's a lot of really good overlap and synergy, which enables us to continue to measure any light source, create any spectrum, or reflect any wavelength. And again, all of those three kind of areas that Labsphere and ILT focus on are tied together with our expertise in test and validation, radiometric and photometric test and validation and calibration services. And so, if we think about the areas that Labsphere sees growing with our illumination sources and reflection materials, relating this again back to analytical instruments and medical devices, we see a lot of growth in the spectrophotometry field or applications, and the applications that we see growing in spectrophotometry are food quality assurance and quality control, agriculture, which is very closely related to food QA/QC, pharmaceuticals, and drug identification or forensics, somewhat related to spectrophotometry, but with a different spectral range is colorimetry, of course. And what we see, the applications where we see a lot of activity there are in things like food packaging, food quality assurance and quality control, and then just color properties for things like paints, textiles, gems, pretty much anywhere where you need to have that colorimetry data in a spectral form. And if we think about what Labsphere is supplying, and ILT as well, into these verticals, it's things like light sources, integrating spheres, OEM integrating spheres and components for those instruments to function as expected. In medical devices, that's another area where we provide light sources and reflectance components. And the applications where we see a lot of activity are in applications like minimally invasive surgery, ophthalmology, and medical diagnostics, hematology, those types of applications. So just to kind of start us out thinking about where we're going, and really setting the baseline for what this talk is about, we're going to just think about the ideal light sources for analytical instrumentation. And again, this applies to many other applications as well. So if we're designing an analytical instrument, the first thing we really are looking for in the light source for that instrument would be a high power, and high power is either, we're really thinking in terms of irradiance, radiance, or flux, whether it be spectral radiometric or luminous flux. So we want a high irradiance, high irradiance, or high flux, and we want that to apply across a broad wavelength range. In most cases, there are certainly specific applications with narrow bandwidth regions for identification, or whatever the application is, where you can use an LED source. But in most cases, people are using broad wavelength range light sources for analytical instrumentation. In addition to that, we want it to have consistent performance over time. So you really don't want your light source behaving, we want repeatability. We want to be able to turn it on one day and operate, and then the next day have it operate in a similar manner. And in addition to that, we don't want to just have consistent, repeatable performance for 5 days straight. We really want that to operate for a long time, so 5,000 hours or thousands of hours. And then, of course, what can be most important to some people is that that light source be cost effective. And so the one thing I want to point out here is sometimes cost effective should not just be the cost of the lamp in and of itself, but what is the cost of maintaining that lamp and making sure that that lamp functions properly. And sometimes it's worth spending more on the lamp going into a device because it performs better in these other three areas. So really, this is a kind of a matrix where you can trade off in one area or the other in order to improve in another area. And so if we just go back to thinking about what types of light sources are used in analytical instruments and the pros and cons of each of those instruments, we could start with xenon lamps. And so in the next 4 or 5 slides, you'll see graphs similar to this. Wavelength is on the x-axis, and then relative power is on the y. Each graph has been normalized to the peak or the max power within the spectral power distribution that you see. And so starting off with xenon lamps, and here we're really thinking about xenon flash lamps. There's a broad spectral response that goes from the UV vis, from the UV out into the vis, and it's very high power. So if you're working in applications that require a solar-like spectrum, the xenon flash lamps are perfect for that. Labsphere uses xenon flash lamps in a UV transmittance analyzer that we build because we require a high irradiance of UVA and UVB light, and we don't need that light to be on for an extended period of time. So the xenon flash lamp is perfect for that. So I'm showing xenon flash lamps, but there are also xenon incandescent lamps, which are good for other forms of spectroscopy as well. Moving on, I guess the cons to xenon lamps are their cost. They are expensive, and their output can be unstable through time. And so those are some of the challenges that we face with xenon lamps. The next up would be the deuterium lamp, which is really an excellent source when you're working in the UV. So you can see here it has, we're getting a lot of power in the 250 to, approximately 350 nanometer or 400 nanometer range, although you'd probably cut off somewhere down here if you were using this in a system. There's excellent UV emission in a deuterium lamp, and it's very stable in its UV output. However, it does have a shorter lifespan compared to other lamps. And, I have it as a con and it says lower power in the visible spectrum, but the reality is nobody's using a deuterium lamp for anything in the visible spectrum. So again, a deuterium lamp is great for something that requires a really stable output in the UV and a high signal to noise ratio in the UV. So most of Labsphere's conversations, and ILT deals with many more light sources than Labsphere does, but Labsphere works a lot in the QTH world, or the quartz tungsten halogen world. And of course we use other lamps, but QTH are the most common. And that's true for a lot of people in a lot of applications. The quartz tungsten halogen lamp has obviously been a very popular lamp in analytical instrumentation and calibration for decades now. And what's so nice about it are these really stable, um, you know, curves that we see that replicate a black body in a way. So here you can see a 2856K curve in orange, and then a 3000 Kelvin curve in blue. And the first thing that really jumps out is the broad spectral range that we see in a quartz tungsten halogen lamp. So typically, you can use a QTH from 350 nanometers out to 2500 nanometers, and sometimes for other areas as well. So it has a really broad spectral range. It's well characterized. We know a lot about quartz tungsten halogen spectral shape. The output is stable when it's either current controlled or voltage regulated, and so we can get a really predictable and reliable spectral performance out of it. The QTH lamps do have a long lifespan in most cases, and they are very cost effective. Again, the limitations are its UV output, and in some cases even the blue output is lacking quite a bit if you want to make a solar light spectrum. But it does kind of make up for that out further in the near IR and further in the viz. Yeah, there's really no UV output that's too much worthwhile. And there's a lot of heat generation. So if you are designing an analytical device, you always have to manage the heat being generated from a quartz tungsten halogen lamp. So, when people are building things like UV vis, near IR spectrophotometers, they're often using a combination of a deuterium lamp with a quartz tungsten halogen lamp in order to cover that broad spectral range and get good UV vis data and near IR and SWIR data as well. And kind of, what's becoming more and more popular in many applications are LED sources. And so, we can't really show every LED out there. This is just one example of an LED. But LEDs are very, the energy consumption is great. So they're highly efficient. They have a very long lifetime. They're very stable. And then I do just want to point out that in some cases, in order to achieve a really stable LED source, thermal management of that LED is important in order for it to perform as expected over and over again, repeatably. And they are safe, right? There's many safety advantages to an LED. There can be spectral mismatch, and what spectral mismatch is and why people look for broad spectral sources is because, if you're trying to make measurements of something that has a broad spectral shape and you're only illuminating it with, even with a spectral power distribution similar to this, there's, it can be challenging to relate the peaks and valleys of an LED back to a calibrated source with good uncertainty, right? So that is one challenge. LEDs are still relatively low power compared to traditional light sources, and then the batch-to-batch variation can vary drastically, and especially in cases where if you're not buying high quantities of LEDs, it's hard to get the same batch over and over again from a distributor. And so what that does is it introduces some variation in either the peak position, the full width half max, areas like that. But LEDs nonetheless are emerging as excellent replacement sources for light sources in analytical instrumentation. And over the next 10 years, we're only going to see LED technology improve. So, you know, LEDs are the future in many ways, but that future is not here today for every application. And so again, this is just kind of looking at a comparison of all the spectral power distributions. You know, the LED could show a lot more. We could show a lot more with LEDs here. And it's just important to note that these are all normalized to their respective max power. So, you know, this is not necessarily a one-to-one representation of the LED output to a quartz tungsten halogen output, but it does really show you the spectral, the active spectral region where each of these light sources has some advantage or disadvantage in application. And so, you know, if we've known for so long that these traditional light sources, you know, LEDs being the new kind of the new kid on the block, um, are so good and we can really depend on them, what's changing in the lamp world? And, you know, if this is based on observations that we've made at Labsphere, and also observations that we hear from customers, and then just the reality of what's changing in the global lamp market in general. And so that's kind of where we'll start. We'll start by looking at the global lamp market. And what we have here are billions of units on the y-axis and then year on the x-axis. And so, and again, the like the different colors, what they represent. So in the blue, we have things like incandescent and halogen. Orange is LFL lighting, and then the gray is LED lighting. So back in 2012, for residential and some commercial lighting, there was the US and the EU implemented the incandescent ban, and that's because the efficiency of LEDs is just so much greater than an incandescent. It doesn't really make sense to waste energy running incandescent lamps for residential and building applications. And so those bans went into effect they started in 2012, and then the full bans went into effect in the US in 2023 and Europe in 2020. Now, many applications are exempt from those bans, scientific lighting being one of them, but this kind of helps set up the story for what we're seeing in the lamp world. So what started taking place, and you can really see this, is, you know, in 2012, the supply of incandescent, and, you know, there's other lamps in here, but we're just thinking incandescent halogen, really started to drop off. And LEDs really started to ramp up. So what's starting to take place in that process from a business perspective is that manufacturers of incandescent and halogen lamps are abandoning the manufacturing of incandescent and halogen lamps in favor of LED sources, which makes a lot of sense if you're building residential light. To that end, however, a lot of the companies that built residential lighting and you know, building lighting and architectural lighting also manufactured the scientific lighting lamps that we were all familiar with and have had to kind of look for replacements for in the last several years. And so if we start now, we'll just look at the market share for scientific lighting, and this is in percentage now on the y-axis and year on the x-axis. And the only big difference is in this graph, the incandescent and halogen lamps are in the orange, they represent the orange portion of the bar, and then the LED is still the gray portion. And so really what we can see is if we think about back to this 2012 ban, when the ban started, you know, it was basically almost all incandescent and halogen light sources for in dominating the market share for scientific lighting. And now if we look at where we are today, and we're here in a few more weeks, you know, the supply of incandescent and halogen lamps for scientific lighting applications has been replaced by LEDs by up to more than 50%, right? So about 50% of that initial supply back from 2012 is now disappeared. And that's, so the remaining supply is what a lot of us are working with, and we have to, so the question then becomes, what is taking place in the remaining supply of lamps that leads us to having this conversation today? And really, as those tier one suppliers leave the industry, the remaining suppliers of lamps, there are remaining suppliers, but what we're seeing is kind of an influx of quality issues, because for whatever reason, we are seeing that now. So the remaining supply of lamps has a greater probability of having some form of quality issue involved with it. And so those issues look like things like filament substitutions and misalignment. Sometimes a manufacturer will just all of a sudden decide to change the filament material on a lamp, which can be, really have a big impact on the output and what the expectation for the lamp is. Misalignments. And again, all of this really matters if you're trying to align an optical system and you're relying on a repeatable and reproducible filament position as part of your optical alignment, and all of a sudden, 20% of your lamps are misaligned, or you're not going to get as good of an alignment on your grading as you would have originally wanted. Of course, kind of going hand in hand with that are beam and uniformity issues. So, what is there a uniform distribution of light leaving that light source anymore through the lens? That's not always the case. And then just general poor build quality. So this is an example. It's hard to see, but there's actually coils touching, poor cementing. And then, this is an example of, filament material not redepositing on the filament itself and instead depositing on the envelope of that light source. And then one that is near and dear to Labsphere's heart is, what is the output stability of that lamp? How does the performance of a lamp change through time? And so we'll go over this graph in more detail in a few slides. But some of the other issues that are taking place have to do with premature failures. And so, this graph is a mortality curve for tungsten filament lamps. This was taken directly from the Illumination Engineering Society of North America. And this is pretty well known, and we relied upon this to be true for several decades. So when you hear rated lamp of a life, what that means is that at 100% of the rated life, 50% of that initial population. So if you had a population of lamps with a 5,000 hour rated life, at 100% of that rated life, or 5,000 hours, 50% of that initial population of lamps would have died, right? They would have failed, and you would only have 50% of your lamps remaining. So that is what rated life means. So when you hear rated life from a manufacturer, that is what they're saying. And so at 5,000 hours, if the rated life is 5,000 hours, you'll have 50% of your initial population of lamps remaining. Statistically, that's how it would work out. Now, so already that kind of does provide some clarity to rated life, but what we observe and what many people observe is the premature failures, right? So you get a batch of lamps, you start running some tests on them, and several of them fail within the first 24 hours. And so why I have is this still true is because it's almost as if it's no longer a nice Gaussian distribution anymore, right? And that we would have maybe this curve is shifting a little bit because of quality issues being introduced in the manufacturing process. Another area where I think we are observing changes, or Labsphere has observed some changes, and I believe many of our customers have observed these changes as well. That's what I've heard from some of the feedback is, what this graph shows us is the change in luminous flux as a percent as a function of rated life, right? And so what what this shows us is that really after 120% of a rated life of a lamp, that lamp's luminous flux should have only changed by 8%, right? And so that's very predictable. And this is for quartz tungsten halogen lamps. Again, this is, if you want to read more about this, you can check out the Illumination Engineering Society Lighting Handbook. I'm referencing the 9th edition. There's another edition. There's a more recent edition available now. But so, what this really, it's saying at 120% of the life, the luminous flux will only have changed by 8%. And that's really promising and it's very predictable. So we can, from an analytical standpoint or a scientific standpoint, we could estimate what the predicted change in our lamps output would be and how that may impact some of our measurements. However, if we look now at some data that Labsphere recently collected, and in this case, we're looking at a 150 watt quartz tungsten halogen lamp that has a rated life of 1,000 hours. And we're looking at spectral flux, not luminous flux now. But what really jumps out right away, or what should really jump out, is this black curve here. And that is the spectral component of 400 nanometers, and the spectral flux of the 400 nanometer wavelength through time. And this is less than 25% of the rated life of this lamp. And what we see is a more than 30% change in the spectral output of that source. So what that says is a few things. One, the CCT, or the correlated color temperature of that incandescent lamp in and of itself, is changing through time, right? And we know that to be true, but it's really changing, right? And this shows how that's changing, because this 400 nanometer band is just dropping off significantly. And also you can see that this red line, which is the 500 nanometer component, is also dropping off. So that would, while we don't have the data, you can kind of fill in what might be happening between 400 and 500 nanometers to a certain degree. And so again, an over 30% change in the 400 nanometer spectral flux within less than 25% of the rated life of a lamp. So if you're building a spectroscopy instrument that relies, and your customer is measuring something in the 400 to 500 nanometer wavelength range, the uncertainty of that measurement is changing through time. As you can see here, because the output of that lamp is changing. And, of course, there are calibration techniques and things like that, but if this is changing throughout the day, it will have an impact on those measurements. And we have seen similar phenomenon in the IR region. It's just not apparent on this lamp here. And so, the hardest thing about any of this really is, you have one 150 watt lamp that behaves one way and another one that behaves another, and it can be hard to make good sense of what different lamps are doing at different times. And so we can introduce a few validation and test methods to help us identify and flag lamps that may be causing these problems, or improve and stabilize the lamps prior to using them in any type of application, really. And so in this, the first thing to kind of consider is seasoning lamps based on LM54. And LM54 is a guide for lamp seasoning, and its intended purpose is to, provide laboratories with a methodology to season lamps prior to making photometric, colorimetric, or electrical measurements and characterizing those lamps. But it's a best practice that can be used for lamps in a variety of applications, scientific instrumentation, or different integrating sphere applications as well. And so the first thing to consider is, if we're just referring to the letter of the LM54, what we would call normal seasoning is operating a lamp at its rated voltage for 0.5% of the lamp's rated life. There's another method introduced in LM54 called accelerated seasoning, and that is operating a lamp at a current or voltage greater than it's recommended, but you run it for a shorter amount of time. And if you refer to LM54, there are several equations that you can use to actually estimate what length of time you would need, how long you should run a lamp at an overrated voltage or current to accelerate the seasoning. You should not do accelerated seasoning on quartz tungsten halogen lamps, however. But what Labsphere has noticed, in order to get lamps to actually perform in a stable manner for applications involving medical devices or other analytical measurements where low uncertainty and stable performance is a big part of the requirement, that we need to extend seasoning time all the way up to 10%. And that's a pretty drastic increase in stabilization time. If you just look at what that looks like for a 5,000 hour lamp, if we just go to 7%, we're already at 350 hours of burn-in time. But what this does, by extending that burn-in time, it allows us to identify premature failures. So you can pick up on whether or not a filament is redepositing on the envelope, so you could identify that graying. And you don't have to do any form of measurement during a stabilization period, but if once you kind of understand how your lamps perform, it will help with stability issues as well. So this, a proper burn-in or an extended burn-in can really get you to your lamps to a stable point of operation. The one thing to note with any type of seasoning or burn-in is that the filament position, if whatever your application is, the filament positioning that you use in your application should be the same as the way you burn in your lamp. And that needs to be, you really need to keep track of that. So then after you've done seasoning, you can always apply lamp screening processes. And what lamp screening is it's comparing, if you have a batch of lamps, you're basically comparing the performance of each individual lamp relative to the mean of that entire batch. And so you can do that with just a detector on an integrating sphere, where you put your lamp in, each individual lamp in, you make sure your power is stable on that lamp, and then you read off the detector current and you compare the current. You look at the current of all lamps, and then you look at the performance of each individual lamp to that mean. So you're really looking at something like a coefficient of variation. And then where some insight is needed on the part of somebody implementing a lamp screening procedure is what is the pass-fail criteria for your application. And that really is something that requires knowledge of your application and how your lamps perform within your system in and of itself. And so you can also do this in a calibrated way using a calibrated integrating sphere spectroradiometer. So the only difference then is you're not just reading off detector current. You either have a calibrated spectrometer on it, or a calibrated detector. And when you start doing that, you can really start comparing metrics like spectral flux, luminous flux, or color temperature. And again, you can look at the coefficient of variation between a batch of lamps and determining which ones are reliable and which ones are just not going to work for your specific application. And so those two methods alone could really help people identify premature failures and stabilize their lamps doing a proper burn-in, and then taking it a step further and doing a lamp screening after a lamp burn-in allows you to really make sure that all the lamps within a batch of lamps are performing in the same or similar way within a defined coefficient of variation. And so, how can Labsphere and ILT help? Well, the first thing to note is that ILT is a lamp supplier. So ILT supplies specialty and scientific lighting or illumination sources for a variety of analytical instruments and medical devices. And those are, traditional lights such as, halogen and incandescent lamps, NDIR lamps. Those halogen and incandescent lamps and NDIR lamps can be mated to custom reflectors. And, that's what ILT has specialized in for many years, right? Is supplying those lamps and providing them with custom reflectors for a variety of applications. Um, to that end, one of the nice things about working with someone like ILT is that because ILT has such a grasp of the supply chain, that they're usually right on top of it when one lamp is going obsolete and they need to spec out another lamp. And, they have a whole team of optical engineers and project managers who focus on making sure their customers maintain a consistent supply of lamps that perform in a given way. And so, and there may be some changes here and there, but the nice thing is ILT takes that stress away from the manufacturer or from like an OEM. And so, instead of being down 6 months while you try to source out a new lamp, ILT can kind of do that in the background. They also supply UV, LED, and custom LED light sources. And then, of course, all of these light sources can be assembled into custom lamps and reflectors. And so, taking that a step further, one of the nice things about Labsphere and ILT together is that, you know, not only can ILT supply the light sources, but then Labsphere and ILT can offer a variety of validation and verification testing. So if you are building an analytical equipment and your yields are low on your light sources, ILT and Labsphere can kind of do some value add services to help validate and test light sources at different points during the manufacturing process. And really taking away the burden for you to do all that sorting, and not just the burden of an OEM, but the burden of the customer. There's nothing worse than sending a customer a lamp and having it, die within the first 24 hours of use, and then just having to go through that whole entire process again. And, finally, Labsphere and ILT have a fully integrated prototyping and manufacturing facility. So, we have multiple machine shops, a full suite of electrical, optical, mechanical engineers on staff. And so we can really help bring a customer from just a light source to a complete illumination source assembly that is drop-in ready for an analytical instrument. And so again, that's really what we're showing here is we can really take people from just a light source to a full assembly that is ready to just be dropped in directly into an instrument. And then finally, one of the things that Labsphere has been doing for decades now, or maybe not decades, but the past decade, is building tunable LED engines for different radiance sources. And so here's an example of, we had a problem that we needed to solve, which was replacing a plasma light source in a system that needed to replicate the 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 albedo basically, and so daylight spectrum. And plasma for traditionally or historically, plasma sources were mixed with quartz tungsten halogen sources in an integrating sphere to produce a solar-like spectrum. And so, but there were some challenges with that. So you can see there's the spikes, there's reliability issues with plasma lamps, and there's even though there's more blue than a quartz tungsten halogen lamp, there's still not a really high radiance of blue photons in that in those sources. So what Labsphere did was we designed this blue spectral source here, which is actually a combination of multiple blue LEDs and some broad spectrum LEDs in order to boost the blue region of that to boost the blue region in a quartz or a solar-like spectrum integrating sphere. And so what you do is you kind of take this blue light and you mix it with a QTH, and then you get this really nice solar-like spectrum that actually is better than the traditional plasma source in the end. It's a closer match. And so Labsphere has been working with these light engines trying to produce broad spectrum light, LED light sources. But the trade-off is the size. You know, to get these high output powers, you really need larger, you need the space to do it. And of course, it's not as inexpensive as a quartz tungsten halogen lamp. And so, yeah, in closing, you know, what Labsphere can really help with is an ILT. We can act as a supplier of traditional lamps and help you test those lamps in the process so you meet your yield expectations. We can act as a manufacturing partner so you can just get a drop-in lamp assembly. If you're developing an analytical instrument, we can really take that burden away from you. And then we can provide design support for next generation replacement sources as needed. And so at that point, we've kind of reached the end, so we can open it up for questions if there are any questions.
Thank you, Lauren. If anybody has any questions at this time, you can type it into the Q&A box. We are recording this webinar, and a recording will be sent out to everyone who registered for today's webinar. So if you want to view it again, or if you have colleagues that couldn't make it, you can feel free to forward them that link. In the meantime, Lauren, did you want to put your contact details in the chat box for anyone who may think of some questions after?
Yeah.
So we have one question that just came in.
Oh.
Oh, I thought it was, nope, that's.
Oh, yeah, Martin, will you please type your question in the Q&A?
I don't think we can unmute. Unfortunately, I can't unmute. Actually, I think I can allow his mic. Do you want me to just allow him to?
Thank you, Mark.
If you want to speak your question, I think you can do that now. If you want to unmute yourself.
Okay, yeah, thank you. I know Siemens, Osram were suppliers of QTH. Who are the big suppliers now of quartz tungsten halogen lamps?
Yeah, so that would be a better question for our colleague Jill Fowler. Jill Fowler is one of the directors over at International Light Technologies. I believe they work with about 7 to 9 different suppliers, depending on the actual source type. But yeah, I think some of the bigger names have dropped out. So that's a lot of the ILT team are former Osram group.
Yeah, Jill's been there for a long time. I know Jill personally. She's been
okay, good. Yeah, Jill's the best one for that question. Okay, specifically. Yep.
If there are any other questions, you can raise your hand and I can unmute you. If it's easier to ask your question versus typing it. Okay, Mark. Looks like we have another question from Mark. All right, hold on. Okay, go ahead. You can unmute yourself.
There we go. So, Lauren, my use case is kind of in a corner, perhaps, but is the 1,000-watt QTH that's has had transfer to NIST lamps, and what I do is I use a spectral on panel and a holder at 50 centimeters to get a known radiance right out of that system. But it's those 1,000-watt lamps that I could have bought from Gooch and Housego. Now it used to be Optronics Laboratories, or even have NIST calibrate directly if you weren't willing to pay for it and get a little bit more certainty out of it. But are those ever going to be made again, or what? What do you know what the status of those are?
Yeah, the 1,000 watts, I really don't. But it's something I will write down and bring back to the product team, for sure. Yeah, I don't think Labsphere is really working with 1,000. We might have so you're using you're using a fell lamp then, right? So a it's a directional lamp. Is that correct?
No, it's like what I use it horizontally as if it was used in a work light. It has an
Okay.
electrode at either end, not two electrodes at one end.
Okay. Okay. Yeah, I was gonna say Labsphere did have the fell for a while, but I'm not sure we would that was more of a directional 2 pi
Yeah.
style source. But it's one thing we can check about. We didn't pick up any of the Gooch and Housego replacement products. Unfortunately, we just didn't pursue that direction
Yeah.
to be.
Well, what I need it basically, I use that wattage because of the radiance that I want in the blue, and then I'll use a KG2 filter to filter out the excess, NIR that you get out of that situation.
What's your
To
end application?
remote sensing, so trying to get the
Okay.
correct upwelling,
Could you use an integrating sphere to irradiate the plant for the panel source? We do have customers that have done that. They use
Well, it's a question of traceability and the number of transfer steps and all of that. So yeah, I know that's one way to do it, but then you got to send the whole integrating sphere back to be calibrated again when it needs to be calibrated. So
there is
whereas
a
just buying a
use
lamp is a lot easier.
I know. I don't disagree with that. So, okay. Yeah. And just as a point of reference, it's not my area of Labsphere's business, but, we do now have a dedicated service department to kind of help relieve some of that calibration, those calibration hiccups that you're talking about, where
Right,
if somebody is using an integrating sphere, so can I just ask, are you doing a direct tracement? So do you have a NIST lamp that you transfer your calibration directly to? So
Yes.
okay, so you're doing your calibration directly to a NIST standard.
Yes.
So if you add in the integrating sphere, you're now 2 steps away, and you're probably trying to get less than 1% uncertainty is what I'm assuming. You're trying to go, what level of uncertainty are you looking for
Less,
in
yeah,
your,
I know anything better than 2% is a challenge, but I do
yes.
like to brag. So and I have to do this every year, actually twice a year
Okay.
and so I don't always have the same lamp available. I don't always have the same power supply available. So I need calibrated sources so I can do this comparison year after year. And
Okay.
it's to demonstrate the absolute calibration of of an imaging spectrometer basically has remained stable.
Yep.
Um, uh, Doing a transfer cal from that NIST standard to a sphere has been
Yeah.
the standard practice. I'm trying to move to the direct observation of the lamp and panel to remove one of those transfer steps and maybe increase some certainty. But this is all
Okay.
based on those 1,000 watt NIST calibrated lamps. And I have several, so I can play a
Yeah.
transfer game between them and just rely on the pool that I have and wait until they time out, and hopefully LED sources will or something will evolve. But it's the illumination industry that drives a lot of this technological innovation, and
Yeah.
they're not interested in NIR or SWIR or anything like that. So
I know. I know. I don't know, Mark, if are you connected with Dan Sharp at all? Do you know
yes,
Dan?
very
Okay.
closely. I just
Oh,
attended this
okay.
because I wanted to see the breadth of what was going on.
Yeah, it's a little bit of a different focus than what you're specifically going after. And now that I see your name, I think I've followed your some of your LinkedIn posts about
Oh, thank you.
calibration for some time. But Dan Sharp would be Dan Sharp is the product manager for the remote sensing
Yes,
product lines
yes.
at Labsphere.
We
Okay.
commiserate ops often.
Okay. Yeah. Because when it comes to like the ILT, that does not really go after those really high power light sources. So if that's not really in ILT's wheelhouse, or it's not
Okay.
that it's not in their wheelhouse, it's just not been a product pursuit. However, this might be a good conversation with Dan Sharp.
Right. Well, he knows it's not a big
Okay.
market, that's for sure.
I know that's the challenge.
Well, I
But
don't want to dominate this meeting here, so I
hey,
think I've diverted it enough.
I really appreciate your question, and thank you so much for joining and participating. Like I said, I do follow a lot of your LinkedIn activity, so
Thank you
I'm
very
happy
much.
for you to ask a question. Thank you.
Oh, hush, I'm blushing.
Martin has his hand raised again, so I'm going to. Oh, your mic is enabled, Martin. If you want to just.
Mark, you should also look at a calibrated detector as well as a deuterium UV lamp.
That's the other.
LIT used to make calibrated detectors.
Yeah, they still
Yeah.
do.
Yeah, and I just found in a case, I'm working at Neon now, and I just found in a case some very fancy, ultra stable radiometers made by the University of Arizona remote sensing group. And so one of my aspirations is to implement that. But going from source-based to detector-based transfer of standard is indeed one way to work around that.
We did have one question come in online. I'm not 100% sure of the questionnaires name, but it is, how can one accurately measure the rated lifetime of halogen lamp under controlled conditions? And what method, Kingston, thank you, Kingston. This question is from Kingston. And what methodologies are recommended for assessing the stability and performance consistency of such lamps during operation? So I think, the question would become, what type of controlled conditions are we talking about? If it's using a light measurement sphere, light measurement spheres can get quite complex. Some of them have built-in, environmental units to control temperature, humidity, everything like that. So there's a testing regimen based around that. So it would really depend on what type of conditions need to be controlled, and to the extent at which the integrating sphere can be monitored to do that, or if there's another testing method you could do that with, if you're, depending on what conditions we're trying to talk about. And as far as methodologies, I am talking about integrating spheres because I'm usually thinking in spectral radiant flux when it comes to measuring light, but there are a multitude of ways to measure light, and a calibrated detector was just mentioned. You can measure irradiance on a calibrated detector. There are a variety of different methodologies. So if I'd be happy to kind of go into more details with that with you, Kingston. If you want to send me an email, I'm happy to kind of continue that conversation, and we can really just address specifics of what you're looking for and how you could implement something. So I'm happy to do that through email. And then it looks like Lana Pride has a question too.
Yep, it's
Okay.
good to see you, Lana. Glad you can make it. Your microphone has been enabled, so you can just unmute and ask your question. You need to unmute your microphone. You need to unmute your mic. Able to unmute it. Okay. There we go.
Yeah, hi, Lauren. Thank you for the excellent seminar.
Thank you, Lana.
I have one question. Yeah, as you know, I've worked for Royal for 26 years, so I've seen it all with all these sources. There is a certain dichotomy, let's say, between if I'm building an instrument, let's say, and I want everything in one box, I'm obviously going to go with a little deuterium lamp and a little quartz tungsten halogen lamp. We tend to do more of the linear spectroscopy system, so we're not limited necessarily by space. Although personally, if I had my personal prejudice is I sort of like, I feel that nothing beats a straight up xenon arc lamp, and the QTH lamp is a little more stable, and those are basically the two sources that we typically deal with, unless we're going out into the far IR. As regards the LED, I have a question for you. As we, you know, we have a large marketplace that we deal with at Oriole, and some of the people really do not like LEDs, like the museum people. They actually have to paint the LEDs, the outside of the envelope, to get the color that they want. You know, very expensive houses and stuff, people are not particularly happy, even with the warmer LEDs, the
Mhm.
light output. So that's an issue, but they always hum, and I don't know that they've solved that problem yet. But can you speak to what you've seen, you know, as regards, like you mentioned, the batch to batch variation and the spectral mismatch and calibration being a problem? Those are things that I see going forward as real sticky issues for LEDs. So I'm interested in your experience, you know, in the real world with these, and what you see going forward.
Yeah, so I would say that you know, one of the things that Labsphere has done because of the problems that you were mentioning is, you know, and I took quite a few slides out of my presentation, but I had more slides in there to show some of the using multiple LED light engines or arrays of LEDs, the level of spectral matching that Labsphere can produce for a target light source. So for instance, we could take a target like D65 and Labsphere, using an integrating chamber and an LED array, will actually combine several different um, spectral components and mix them to produce a D65 output. Now, of course, there still will be some, you know, there still will be a little bit of peaks and valleys, but in order to assess the level of spectral matching that we can produce using our light engines, we have a metric called A prime, which really just looks at the area between, you know, it's just looking at the area between a target spectrum and the spectrum that we reproduce. Because, yeah, I mean, the reality is, you know, depending on what lighting is the light source is being used for, you know, in if we're thinking about architectural lighting, right? You, lighting manufacturers have a metric called CRI because of the way LEDs
Right.
render color, right? And so, you know, a red could look brown or something like that, right? Because it's just such a horrible spectral output from that LED source onto reflecting off of some form of clothing. And so it's actually a very similar experience to that, except when we're talking about spectral mismatch between you know, a target, if we want to actually get some true spectroscopy data from it, you know, if the energy being put onto the surface is not, you know, it's hard to say spectrally flat, right? Because a QTH is not spectrally flat. A deuterium lamp is not spectrally flat, but the energy is going across in a pretty even band, and it's very predictable. Versus with it, if you're using an LED and you get a peak, you know, you're really going to get some mismatch between what you're using for the excitation source and what you get back on your spectrum or your reading. And so I think we probably have some data to show the impact of that, and maybe based on your comment, I'll add it into the slide next time, just to kind of show what some of that spectral mismatch actually looks like. You know, Labsphere is often working in reflectance values. And so that's often what we're thinking about spectral. It is still spectral reflectance, but you know, we're thinking in reflectance units. But I hope that kind of answered your question. I don't know if I went around in too big of a circle or not, but I hope that kind of answered what you were
Yeah,
asking.
it does. It's just that my experience with LEDs, let's say you have an instrument, you've made an instrument and it's oh, I don't know, a spectroscopy instrument, and you have all these different LEDs, and each LED, you have all these overlapping wavelengths to do your wavelength selection. What do you do? I mean, what's the probability that any one LED is going to burn out? I mean, in real life, they burn out. there's, you're building an instrument. Yes, you can take a big batch and you could do, you're basically picking LEDs to do what you want and testing the LEDs and doing the final test yourself. But then once it goes into the instrument, I'm uncomfortable with if one LED burns out, what do I do? Then my whole instrument is off. If I have a xenon or a QTH or a deuterium,
Yes.
I simply open the lamp housing and change the bulb.
Yeah. So you're okay. So that's a really good
That's
point,
that's
right?
sticky, and that's sticky.
Yeah.
That's the real world. That's what exists.
Yep.
And our customers,
Yeah.
I can only speak to Oriole. By the time they get a light source installed and set up, they don't want any changes other than changing the lamp. Okay, you don't want any changes. Okay, you can concentrate on your research, but that's what I'm very uncomfortable with, because I know in the real world, LEDs burn out. I mean, anybody with a house, you put in a bulb, it tests 10,000 hours. A couple months later, it's gone.
Yeah.
So.
Yeah. And, and I mean, there's ways you can use, feedback loops and characterizations to help overcome that. And that's, when we're talking about some of the integrating spheres, that's what we do. We use feedback loops and characterizations. So if something like that did happen, it would be obvious, but it's far less, I can't think of one case where it's actually happened yet, where just like, like just one LED has died, because their reliability is so much. They are more reliable. But again, though, the other flip side of it is you need more in order to get the powers needed for many of these measurement types, right? So you need a larger array, but with proper characterization, and which is a procedure that needs to be developed, right? Those things can be identified. So, all right, we are kind of getting to the top of the hour, Maria.
Yep. So
Okay.
yeah, we are actually over time. So if anyone has any additional questions for Lauren, please take down his email address and you can reach out to him directly. And we thank you so much for the interactive Q&A. This has been great.
Yeah, I really appreciate everyone's questions, and I really appreciate everyone taking the time from your day to join us. Please feel free to email me. I'm always happy to learn more from our customers and, just improve in general. So feel free to email me to continue our conversations. Thank you so much.
Thank you. Bye-bye.
Lauren, can I talk to you on the team or after?
No, not
Okay.
on this call, sorry, because it's being recorded. So,
okay.
Yep.
All right.
But I can set something up with you real quick. Okay.
All right.
I can probably call you from Teams right after this. All right.
All right.
Thank you so much.
Bye.
Bye-bye.